Yeah, thank you very much for coming to my talk. Today I will present a framework for data mining in wind power time series, which is the main research focus on the applied research focus of my group. A bit louder, of course, yeah. I'm a junior professor in Germany, supervising a small group of 4 PhD students, and our topics are computation intelligence, which means machine learning and evolutionary computation, and we have applications in various domains, but the most important one is wind power and solar power prediction. And today I will present a framework that we programmed for connecting wind or machine learning algorithms to wind power time series. The motivation is, as we all know, in particular in Germany, the amount of wind power is increasing. The renewable energy sources are growing. We have an estimate or an objective of having 35% of integration of renewables in 2020, and this goes up to 80% in 2050. What we think, or our motivation, is that data-driven wind power prediction is the future, not only, or maybe a combination with numerical weather predictions, which are currently mainly employed for wind power prediction. And what we tried to is, or what we wanted to do here is to connect or to program an easy-to-use framework that makes it easy to access machine learning algorithms and to combine them with wind power time series. Here's a short overview of my talk. After a short introduction, I will present the framework and in particular concentrate on the modules, basic statistic modules, wind energy prediction, of course. Then we have some special topics like RAM prediction. RAMs are if the wind suddenly goes down or up. Then we have some modules for some methods for data repair and also monitoring with dimensionality reduction. And finally, I will give an overview of the research we are doing in Oldenburg, the further research. So here's an overview of our framework. What we offer is adapted machine learning methods that are adapted to wind power time series, in particular concentrating on tasks like classification, regression, clustering, and dimensionality reduction. And I will give examples for classification, regression, and dimensionality reduction today. Our framework builds upon Python, which makes it easy to prototype ideas fast. NumPy, which is a special package within Python, SciPy, Matplotlib, and scikit-learn, which is the basis of many machine learning algorithms, easy to access. It's like VK, but for our purposes, much better even. But we also have a set of own implementations of our methodological research on machine learning. The framework is released with a BSD3 clause license, so it's openly available, and you can access it easily via windml.org. It's on GitHub, and I want to motivate everyone who listens to my talk or reads my papers to develop with us, because you can easily write own packages, own modules for the framework and integrate them. And we combined the methods to wind time series data like the NREL data. I will introduce it on the next slide or the slide after that, and other openly available wind time series data like AEMO from Australia. But we are also collecting wind data which is freely available. For example, we have some scripts that collect data from airports in Germany, wind power data, and wind strengths. So here are some particular details about the framework. For example, we store the data in the NumPy binary file format. An interesting thing is that if you install WindML on your computer, and you run some commands, some methods, only the data that you requested are downloaded onto your computer and used. For example, if I have a method like load wind from Tehachapi from January 2005, then I will only get this particular data, and you don't have to download everything onto your computer. Every method you implement will produce a rendered example if you integrate it into WindML, which will be put onto our web page. The output of the scripts will put onto our web page and the graphics as well. So if you have implemented an interesting idea, then we will of course review it and then put it onto GitHub, and then it will be automatically rendered and presented on the project website. Interesting is, or the most important thing of course, is to have large sets of data, and our main focus is on this data set. This data set, which comes from the National Renewable Energy Laboratory, shortly NREL, and it offers measurements of about 32,000 wind turbines, partly based on measurements, partly based on simulations, and it is available for 3 years, 2004 to 2006, and it employs a graphical user interface. You can browse through it like Google Maps, and with a right click you get information about the turbines, and you can download the wind power time series of this particular turbine. But we mirrored the whole data set on our server, and which is about 2 or 3 gigabyte wind time series data. And the important is the resolution of the data. It has a resolution of 10 minutes, so we have about 52,000 entries per year. All other further data sets can easily be integrated into this framework. Now, what is the advantage of this framework? First, we have a pre-processing package. This allows us, for example, to fill in incomplete data. If we have missing data, it can be repaired with imputation methods. We have special methods like the Haversine distance between coordinates. If you need, for example, all turbines within a radius of 20 miles, you get this with these special methods, and you can, as I already mentioned, employ commands like select the wind turbines in a specified radius, for example. On the right-hand side, you can see a screenshot of our project website. But later on, if we have time, I can show you some things directly in the browser. So now we come to the modules. The basic modules, or the first part of modules, consists of basic statistics and visualization methods. For example, we can generate features from the wind time series. First of all, of course, the features that we generate from the wind time series are the most important things. Then we can make statistical surveys of wind power or REMs and other properties. And we have some methods for visualizing, for example, for visualizing the data. Here we have an example where we compare visually 7 time series of 7 turbines. Here we have a histogram of wind speeds for a park or for a turbine in Cheyenne. And yeah, these are easy methods that allow us a first impression of the data. But of course, most or more important thing is the objective of data-driven wind power prediction. And the basic idea of our approach is to treat it as regression problem, of course. Regression problem means we map some patterns to a continuous label. The continuous label is the wind that blows in a given time range, in a time horizon. And we employ some kind of spatial temporal regression model, which I will explain in the following. So what we need in regression problems is a training set of pattern label observations combinations. So we have patterns here. These are vectors of features, and we have labels. And with this training set, we can train the models. So we seek for a regression model that maps from our data space. Let's say it's RD, R to the power of D, and we map it to wind power in the future. And of course, the question comes up: what kind of measurements can we make? What kind of features can we collect and put into our regression model? The answer is the target turbine, the time series of the target turbine, the short history and of the neighbor turbines, which makes it then a spatial temporal approach. And the labels are the target power values we are interested in some future t, if we are at time t, some future t plus lambda. To make it more easily to understand, I have a visualization here. Assume we have a target turbine we are interested in, how much wind blows at t plus lambda. And we have some surrounding turbines, T1, turbine 1 to turbine 4. And each has, at a current time t, which we know because, of course, we have all measurements until current time t. Then we can put into our model the following features: the wind at time t of each turbine, the wind at time t of the target turbine, and maybe the past 1, 2, 3 measurements. And this is the basic idea. So each feature, each pattern now consists of the following d features: the wind that blows or that is measured at the target turbine, and the wind of the neighbor turbines, and maybe if we can put it into the model and it approves the predictions of mu up to mu past time steps. What else can we do? We can of course compute some further features like the changes, wind power changes. For example, the wind power change from one at point t to t minus 1 or vice versa can be another feature, and we just put it into our pattern, and finally we got this pattern label combination. And this works quite well. What we then employ is nearest neighbor, for example, k-nearest neighbors, or support vector regression. And here we have an example with k-nearest neighbor and support vector regression, and threefold cross-validation for a turbine in Palm Springs with a certain ID here, ID 1175, which is not important. We employ turbines in a radius, 15 turbines in a radius of 15 kilometers. And we train with the first half of 2006 and test on the second half. And this is what comes out, but be careful if we see some such plots, because our model that we have to predict is the so-called persistence, which means that the wind blows at time t plus lambda as much as it blows at time t. So just shifting the curve, the power curve. Let's have a closer look. Y is the plot how the wind is actually blowing, and PSD is the persistence model, which is just shifting it by time horizon lambda. And broadly speaking, it makes every movement higher and up, up and up down, like the actual power curve, but of course there's not much information in it. But unfortunately, the wind changes are rare, so the error we get with the persistence model is quite low in comparison. What are we now interested in? Of course, improving wind up and wind down predictions, and this works quite well. On the right-hand side, we see the errors that we make, so the difference between the actual power curve and the predictions. And here we see the same result for the support vector regression model. I said it works quite well. Well, let's have a look at the, oh no, it's not working anymore. I have to leave this zoom kind mode to be able to use the keyboard, yes. So here are some numerical results. The persistence model achieves an error of 185, whatever this means, but we can compare it now to k-nearest neighbors, which achieves a lower error with a certain neighborhood size. The optimal neighborhood size achieved by cross-validation is 20, and the best neighborhood size is 20 years, and the error is lower. And we can also further improve the wind prediction with support vector regression and the following settings, which are of course not important and problem dependent, but we can decrease the error further. So the error, we get better values than the persistence model, which is quite fine at first. But of course, we are interested how does it perform in comparison to numerical weather prediction models? And the answer to this question was not easy in the past, because we did not have, for the same time and locations, for the same time range and locations, we didn't have the same data. We didn't have data for the turbines and numerical weather predictions until this year. And I can now show the results here, which will be presented on the European Symposium Artificial Neural Networks in Brugge next month. It looks as follows. We have the numerical weather predictions from Forwind, which is a large wind institute in Oldenburg of my university. And they buy the predictions from the Deutsche Wetterdienst, which is a weather forecast service. And this data is called Cosmo.de. DE stands for Germany, and consists of 20 ensemble members. An ensemble is a numerical weather simulation, and they employ different starting conditions, 20 different starting conditions of the atmosphere, let it run, combine the result. They have a statistical post-processing in the end. It's called the calibrated model. And we have the same data. Now we have wind data for the same time range and for the same area. And we get the following results. We can see here that the support vector machine, the support vector regression model, always achieves a lower error, not always, but in the first 2-3 hours, then it is outperformed by the calibrated numerical weather prediction. So you see here the uncalibrated raw prediction that comes from the Deutsche Wetterdienst. Then we have the calibration by Forwind, which is state of the art. They really sell it to actually. And then we have our predictions for the same locations, and we are better in the first 3 hours. Unfortunately, we are not able to earn money currently with this model, although we are better. Why not? Because I'm not a professional in startups and everything. Maybe I should do that in the near future. The next idea that came up was to combine both models, and actually we could even improve the prediction by simply combining it with by linearly weighting the predictions. So we say alpha times numerical weather prediction plus 1 minus alpha times our support vector prediction, and we can then test various values, several values for alpha, and then we can we have some optima here. We can see it here in this picture for different time horizons. We can see that we have an optimum here. This curve always has a lowest value, which is lower than the raw numerical model or the raw support vector regression model. And yeah, this was also quite satisfying to see that we can improve it with this simple ensemble. Of course, there are other ensemble methods that are possible, for example, stacking, using the numerical weather prediction as feature for our support vector regression, but this is subject to ongoing work. Other kinds of, this was the part for the directly regression-based wind power prediction. If there are some questions, feel free to ask them now. Of course, you can also later ask some questions.
Slide 13.
Yeah.
I mean, your algorithm is better with a horizon of 3 hours, right? And
yeah.
Afterwards, the other algorithm would be better.
The numerical weather simulations.
Then simply makes sense for the first 3 hours just to use your algorithm, and when I want to have a longer forecast to use the other one?
Of course, it makes sense, yeah. It does not make sense to employ or to use our algorithm for larger time ranges.
Yeah, and in the slide afterwards, you will show a combination of the two. Did you also compare it to the basic ones?
To the what? To
your approach and the other one? So
yeah, it comes when you use these value for alpha. For example, for 0, you get the raw support vector method, and for 1, you get the raw numerical weather prediction model.
okay.
So this is the time horizon is 1 here. This is a support vector model. So alpha is 0 here, and this is the other model. Okay, now I switch to ramp prediction. A ramp, we define a ramp as a sudden increase or sudden decrease of wind power, and then we treat it as classification problem, because then we get not a numerical value, which would be a regression problem, but now we get 0, for example, for no change, -1 for ramp down, +1 for ramp up, and we can build our patterns in the similar way or in the same kind of way like I introduced. So a wind change from time step t to t plus lambda is a ramp up event +1, and we have to define it with threshold theta. So then we can treat it as classification problem, and the results are quite interesting because we have a highly imbalanced classification problem, which is not useful in practical applications indeed, because a ramp is rare. Usually a ramp people are interested in occurs once or twice a day, and this is a classical imbalanced classification problem. We have about 100 or hundreds of no ramp events a day and 1 or 2 ramp events, and although our classifier is achieving an accuracy of 99%, this is not useful in practical applications, because we sometimes predict a ramp where no ramp is, and vice versa. So highly imbalanced problem, which we should tackle with imbalanced machine learning methods in the future. Just a short explanation of this figure here. It is an analysis of the number of features that are useful in this setting, and it is based on the so-called recursive feature elimination algorithm, which employs a linear support vector machine and twofold cross-validation. And we can see that as more features, the more features we employ, the better we are concerning the cross-validation score. Okay, but this is an ongoing research also because of this imbalance. Data repair was another topic I just mentioned. Data in practical applications, of course, the patterns are often incomplete due to, for example, due to sensor failures or other reasons. And the problem is that, of course, then we cannot employ the standard regression techniques. The question comes up: can we still use the spatial temporal relations in our model for a better data repair? And the answer is yes. For example, if we employ the following model here for the NREL data, we simply randomly destroy the patterns and data missing at random for 2 turbines left in Palm Springs on the right-hand side in Reno, and we can see that, of course, the MSE is increasing, but when we employ nearest neighbor regression, we can keep it quite low, surprisingly low, when we're repairing the data with k nearest neighbors, which is, by the way, a very strong but simple model, interestingly. Why is monitoring marked here? Okay. Almost the last topic I will, or the last module I will introduce to you is the monitoring of high-dimensional time series, which is one of my favorite topics because I'm very interested in dimensionality reduction. And the idea is the following: can we visualize the high-dimensional time series? If we have 100 turbines, we have a 100-dimensional time series. Can we visualize that? And the idea is to map this high-dimensional space to a low-dimensional space, for example, a 2- or 3-dimensional space, and employ the colors for visualizing the time series. It works as follows. First, we have a training set here consisting of our patterns. I explained how we can construct them. And then we map, for example, with methods like locally linear embedding or isometric mapping. We map this space to a low-dimensional space, and then we get for each pattern a low-dimensional candidate. And this can be, for example, this position of the candidate can be used to colorize the time series. How? If we map it to values between 0 and 1, this can be an RGB value, for example. If we map it to a 3-dimensional space, each new coordinate is an RGB value. And then we can go through the time series again, and for each high-dimensional pattern, we get now a color with this low-dimensional candidate or a counterpart. And this is what we say here. We have for each, for example, in an unknown time series, for each high-dimensional pattern, we seek for the closest representation and employ its low-dimensional candidate to visualize the time series. And what we see here are two examples on THP on the left-hand side with ISOMAP, on the right-hand side with LLE. And this is the time series of 1 year here. So each row here is a quarter of a year, three months. So we have a whole year here and see the visualization. Interestingly, we can see differences in summer and winter, and we can see, for example, that the wind is changing a lot in, for example, in autumn here or in spring over there. And yeah, is this really useful for analyzing the time series? Yes, somehow. For example, we can use some training data from here, but not too much training data from here. Then we should prefer to use training data from there, where many changes appear. So this can be used for designing the training set. The last thing, which is not currently part of WindML, but which is an ongoing new research, is the turbine placement. So where do we put a turbine? And we did some research with this regard, also based on the Cosmo DE data I used for the comparison of the numerical weather predictions. We have an improved wind wake effect model. So this is distribution of wind at a turbine in a location in Lower Saxony, where I come from, or where I currently work. And we use this data to model the wake effects. Wake effects are a wake effect means that the wind is changed when caused by a turbine, the normal model or the standard model from Kusiak, which is usually employed in this context, shows some local optima, and we have an improved new model, which I will not explain in detail in this talk here, but just to give an overview. And the other contribution we make is we model geological constraints by taking into account OpenStreetMap data. OpenStreetMap data is easily accessible, of course. We downloaded it to our WindML server, and now we are able to model these as constraints. Buildings, streets, and everything are constraints. So the question comes up, if we have some wind distributions here from the Cosmo DE data, which is visualized in the background, and we have some geological constraints, where to place the turbines when considering that they are disturbing each other, called wind wake effect. And this is a black box, a difficult black box optimization problem. Black box means that we don't have the derivatives, and we use evolutionary computation, for example, CMAES and other related algorithms to place the turbines. So, for example, if we have 50 turbines, it is a 100-dimensional optimization problem with constraints, which makes it quite difficult. And here we have a comparison of algorithms. We use simple algorithms like the 1+1 EA, more advanced like the covariance matrix adaptation evolution strategy, and we also proposed some new algorithms that incrementally construct a solution by first taking one turbine into account, then a second, then a third, and so on, until we have a full map of turbines. This is ongoing research. And now I come to the conclusion. We have a new release, or will have a new release of our WindML implementation soon. We invite you to develop it with us. And some references, if you are interested in, on the CEC. This year we will present an evolutionary feature learning on the AIII. In January we presented an ensemble of predictors. On the ECML we presented the WindML framework, and in the New Computing Journal we introduced this prediction model, which was, by the way, developed in 2010 here at the Institute by me and my colleague Fabian Giesecke. And maybe tomorrow we will get, when the notification of Gecko comes, we will know if our turbine placement approach will be accepted. And just a short remark on other topics in my group. I'm focused on stochastic incremental solution construction of dimensionality reduction methods. I introduced a method called unsupervised nearest neighbors, but this can also be employed to supervised labeled data, so dimensionality reduction for labeled data. We are also strongly interested in hybridizing optimization methods for unsupervised kernel regression, which is a special class of machine learning for dimensionality reduction. And evolutionary computation is one of my favorite topics, in particular parameter control, as evolutionary algorithms are highly depending on, or the success is depending on the proper parameter choices, constraint handling, and machine learning in evolutionary computation. So if you're interested in these topics, please contact me. And this is what my talk. Thank you very much for your attention. Do you have questions?
It seemed like everything was going very well except for the ramp prediction part.
Yeah.
And there are a lot of situations in which there are rare events that people want to predict. Is this situation that you're having a lot of trouble doing that, is that common to all those situations, or do people have solutions for other things that don't work in the case of ramp prediction?
It seems to be quite, yeah, the imbalanced prediction problem often occurs in many situations, in particular when considering rare events of wind and also solar energy. So we don't have a good solution until now. I think we couldn't improve it by collecting other features that come from other sources, not only from the raw wind time series, for example. If we had additional information from numerical prediction model, for example, or from satellite data where we can observe the clouds, maybe we could then improve the prediction accuracy further. But I mean, from the machine learning perspective, the idea came up that the problem is not easy to solve. The problem is almost impossible to solve, or at least with the data situation we currently have. You had a question as well? Doris? Yeah.
Do you have any idea how local your data has to be to give you a good prediction?
Of course. That's
how much distance is between the numerical weather?
Yeah. I mean, this is one of the most important or interesting questions, because whenever my PhD students are really upset with the situation to improve the predictions further, I say, imagine that you have some kind of very detailed measurements, spatially and temporally. Then you could vary, for example, in this room here, the movements of all the gas, the atoms here, or the molecules here. If we had such measurements in a very high resolution, we could probably be able to predict the next 1 or 2 seconds of gas molecules, position of gas molecules in this room. And the question comes up: what kind of temporal solution do we need, and what kind of spatial resolution do we need to still have a good performance with these methods, and how far we can go into the future, and how does it compare with the physical models? Because the physical models, they have a direct representation, but they cannot represent everything, because reality is much more complex than the models employed there. So the interesting question comes up: what is the trade-off? What is the resolution we need? What is the time horizon we can employ? And how does it compare to the physical models? This is a really interesting question. And if we only take into account our turbines here, we have it only on. We have a 3D atmosphere, of course, but we have mapped it somehow, or we only use information from one or a 2D surface with temporal and local resolution we have. So we can only use what we have, but having more data would probably improve our models. The question is how. And an interesting research direction could be to use a very restricted but physically understood model of, for example, fluid dynamics or something like that, and then try to scale this. So this would be an interesting PhD thesis, for example, or interesting research to compare this and to learn what can we predict with machine learning here, and where are the constraints. Future work.
Is this going to be most useful with new farm builds? I mean, this type of software is a good prediction of if I have to build a new farm somewhere, what I'm going to get out of that geography. Or are you thinking that existing farms can use this to optimize their existing?
Yes, the turbine placement could be used for everyone, I think. Everyone who plans a new wind farm or wants to modify an existing. And the predictions are not only interesting for these people, but also for market analysis, for example, or for not analysis, for behavior, selling energy and buying energy and other stuff. So I think there are many application areas for that.
Where does this RAMs occur? Is it then just locally, or can it be that a whole region can have such a RAM?
It can be. It can be. There are different types of RAMs. Some are occurred by weather. Some are. Some come because of changing weather situations. The others come, for example, if there are sudden dropouts because the wind turbines have to be, the mechanics has to be protected. They are cut off, so they are, for example, controlled so out of the wind, so that they don't face the wind, but they are.
When it's a big RAM for a region, then the energy providers are probably highly interested in that stuff, right? Because
they are very
they
interested.
can adjust their networks and their power production accordingly.
Yeah, that's right. So very interesting. One of the most interesting problems is the RAMs. Are the RAMs, of course, is the RAM prediction problem. But also one of the most difficult ones. As you have seen in the case of the regression problem, you can the most interesting parts are where the wind changes, of course. We are currently also working on introducing a new measure that only concentrates on the changes of wind. So as always, the persistence makes the models seem to or be better. They look better than they are, and this measure should concentrate only on the changes. Recently, I saw a talk on a conference where people were proud of their predictions, and they have shown plots like me, but they learned the persistence. Indeed, it was a shift by the time horizon of the persistence, and it's not useful in practice. Persistence is okay. Then thank you very much for your attention and for coming.